Yeah, thank you for having me. All of this stuff is a piece of my yet-to-be-written thesis under Martha Prekup and John Shereshian, so they deserve some credit for all of the help they've given me in that respect. Cool. So to start, oh no, I think closing it may have done something. Not that. Okay. All right. So a variety is GKM, and I'm not going to define it very explicitly if it has a sufficiently nice action of a torus on it. What's going to be important for what I'm doing is I want finitely many torus fixed points, and I want one-dimensional orbits connecting those torus fixed points. GKM varieties include much of what we've seen over the past week and a half, give or take. Schubert varieties are GKM, flag varieties, and permutahedral varieties, and many, many more. If a variety is GKM, then we can give a combinatorial description of its T-equivariant cohomology from the data of torus fixed points and one-dimensional torus orbits between them, called the GKM graph. Now, what does this look like for the full flag? Crashed again. I'm so sorry. Is it? All right, okay. So for the full flag, what does GKM tell us? It says that its T-equivariant cohomology is isomorphic to every element of the symmetric group is going to be given an assignment of a polynomial. What are the conditions that they have to satisfy? If I have an element W and I right multiply it by a transposition ij, so I'm switching positions, then that has to be divisible by twi minus twj, which is the corresponding left multiplication. And that has to happen for every element of the symmetric group and every transposition for the full flag. And I'm going to call such an element a spline, such an assignment a spline. I did promise a graph. Yeah, it doesn't do it on here. I did promise a graph, so what does this look like for S3? We have our strong Bruja graph. Every edge up there exists because it is a right transposition, and the labels that I've given, single, double, and dashed, correspond to which left transposition differences along that have to satisfy. So 132 to 312 exists because of right transposition by 1, 2, and it's labeled T1 minus T3 because it switches those numbers. So how do we build a spline on this graph? Well, we could do something a little silly and put the exact same polynomial at every single vertex, so every difference along an edge is going to be 0 and kind of tacitly contained within that ideal. But we can get a little bit more complicated. It doesn't have to have full support. This one, if you notice, is supported at 2, 1, 3 and above in Bruja order. That is no mistake for a Schubert conference. And here is a third example of a spline on this Cayley graph of S3. Now, a couple of the important properties of the T-equivariant cohomology, or the ring of splines, for the full flag. First, it's a graded polynomial module. So if you multiply the same polynomial at every single vertex, our differences aren't going to change, at least not divisibility. It's freely generated by equivariantly Schubert classes for opposite Schubert cells. Everything that I wrote on the past 3 slides were examples of that give what's called in this context a flow-up basis. And the degree sequence, which is probably not what one would call it in this particular context. What I mean is the minimal number of homogeneous elements I need to generate each graded piece is given by how many permutations are of a particular length. The second kind of running, more classical example that I'll have is the permutahedral variety, and you'll notice that it is essentially the same all the way through, except now I'm only allowed to multiply by simple transpositions. So I'm not allowed to hit every single one, and the associated graph is the weak Bruja graph, which I have here. You'll notice it looks exactly the same. I've just removed a couple of edges. And we can also build splines on this one. Now, I guess important piece to notice here, if I were to add in the edges that you saw for the full flag, this would not be a valid spline. Generally speaking, fewer edges, more splines. Goal for me, what this project is kind of getting at, I want a combinatorial generalization. I don't want to need this construction to come from some T action on a subvariety of the flag variety. So what I'm going to do is I'm going to get a simple graph on 1 through n, and I'm going to conflate the edges, ij, with transpositions, ij, in the symmetric group. And I'll let G gamma be the Cayley graph of Sn with generators, edges of gamma. So every edge is going to be right transposition by whatever subset of reflections I choose. And the definition is going to look exactly the same for the ring of splines. I'm just using the edges that I picked in my graph. Now, what does this look for the examples that we saw before? Our full flag is going to look like the complete graph. I'm able to use every single one of them. The permutahedral variety is going to look like the path, because I'm only allowed to flip simple ones. And something that's worth mentioning, if not simply because it's where I got motivated in this project from, if you have a regular semi-simple Hessenberg variety with a regular semi-simple element S and the Hessenberg function H, the kind of natural graph that, well, I say natural graph that you'd construct from H. If you use that, then it gives you the T-equivariant cohomology of that regular semi-simple Hessenberg variety. So, how do we build these graphs not from geometry? Well, I've chosen here the claw, so I'm allowed to multiply by 1, 4, 2, 4, and 3, 4. And I'm going to start with the identity, and I'll hit it with right multiplication. And then I'll keep doing that. And then I'll keep doing that again and again until I run out of all of the edges I need and all of the elements of the symmetric group. And what you eventually get is a picture like this, where I've tried to put the labels in as readable positions as possible. But this is like the analog of the weak Bruja graph. I suppose it's important to mention that I'm working, right, that this is a tree. So the idea is, right, I want to generalize ideas that I have about the path with motivation from the permutahedral variety. I want to generalize ideas that I have about the complete graph motivated from the full flag. So how do we build splines on this? Well, one thing we could do is really just focus on the support, pick some elements that you see up here, and try to make a spline supported on only those elements. So if I were to pick those, right, which I've done purposefully, so that is a coset of a reflection subgroup, right? So now I'm only allowed to multiply on the right by 2, 4, and 3, 4. So I'm only allowed to switch the second and last and third and last positions. And if I were to zoom in, those are the elements that I would get. How are we going to build a spline? What transpositions are we not allowed to use? which is essentially going to be what edges are coming out of this subgraph in the big picture that I had before. So for the bottom one, we can't hit it with 1, 4, which would switch 2 and 1, so I'm going to give it T2 minus T1. Over on the right, on the bottom for 2, 4, 1, 3, we can't switch 2 and 3, so I'm going to hit it with a T2 minus a T3. And I'm going to kind of define by example, but I would posit, right? If you have a coset of a reflection subgroup, oh, because that's a typo. Yeah, at least one. Thank you. Yeah, that's supposed to be T2 minus T4. Yes. Oh, maybe that's where my mistake lies. It's supposed to be 2, 3, 4, 1, making my vertex wrong, but my spline correct. Well, anyway, given any coset of a reflection subgroup created in this way, there is going to be a spline. A natural definition of a spline, I'll call those coset splines, and proposition myself, perhaps I should sell myself short and call it a theorem, but either way, the collection of all coset splines generates R gamma, the ring of splines, as a module over the polynomial ring. And moreover, the linear coset splines are going to generate R gamma as a ring. Yes. So, and if you start playing with these problems computationally, like trying to do this stuff by hand, working with support is really the way to go. It's really hard to get a handle on it if you don't try. Like, for the last one, the best way to see how this expands is to try to make it 0 at the identity, and then try and make it 0 next to the identity, and kind of propagate that up. That's at least the best way I know to try and find some sort of minimal generating set, which this is definitely not. This is way too big of a generating set to be minimal. But it is homogeneous. Now, lemma, or fact, I suppose, for any graph, gamma on 1 through n, the ring of splines is a graded module, which I've kind of, at the very least, hinted at thus far, but it's not always a free module. It is also a graded SN module via the dot action, which is, I put in there because it's part of my motivation for it, but I won't get too heavy into the details with that. And I say proof, or at the very least, example of why it's not always free. If you take gamma that I had before, then R gamma is not a free module, right? And the degree sequence, how many generators I need in each degree to create a minimal generating set is 1, 9, 15, 1. So I need just one constant spline, 9 linear ones, 15 quadratic ones, and only one of cubic. Module generators, yes. Yeah, ring generators, I just need the 1 and the 9. Because it's a subset of the coset splines that I have before. Yes. So I suppose 2 things to notice about this sequence. First, it's not palindromic, which is the easiest to see. Second, there's more than 24 things, which is how we know it's not free. Also, I computed it by hand, and I also plugged it into a computer program that told me it wasn't free. But triple checked, this is definitely not a free module. And going forward, I'm going to superscript with an I to say the ith graded piece. So this is, I suppose, right, this is my generalization, at least what I'll tell you about my generalization of the path case. No. Scratch that. So sorry. So I've given you what I can tell you about the path, or at least trees at the very least. Now we would like to characterize for which gamma the ring of splines exhibits flag-like behavior. And I would say that, right, we're going to need a definition for this. A graph gamma is k-connected if the induced subgraphs formed from deleting any set of k-1 vertices are still connected. So we can't cut our graph into 2 or more pieces by removing k-1 of our vertices. As a quick little example, the one on the right is 2 connected because we can't delete any one vertex to disconnect it, and the one on the left is sort of obviously not. This turns out to be an exact characterization of when the dth graded piece of a ring of splines is equal to the one for the complete graph, isomorphic to the t-equivariant cohomology, the flag. So a graph gamma is k-connected if and only if the modules at the dth graded piece are equal to the one for the complete graph for all d strictly less than k. And as a corollary, if gamma is k-connected, then the dth graded piece of our gamma is going to be spanned by the equivariant Schubert classes that we got from just the cohomology theory. How does this look like in an example? Well, we can go graded piece by graded piece, and this graph is not disconnected, so it's 1 connected. And the constant spline does span that 0th graded piece. We also can't delete any 2 vertices. We can't delete any 1 vertex, we can't delete any 2 vertices. But we can delete 3 to disconnect this graph. If we take out the red ones, we're going to be left with a solitary vertex on the lower left and a 4-claw on the upper right. So what does that say? We're in unfamiliar territory. There are more splines in the cubic piece than we can get by just looking at the Schubert classes, is the idea. So this is my last slide, my advertisement slide, I suppose, right? So incoming, still cooking a little bit on it, but generators and, in particular, the dot action on the first graded piece. I know I can do it for trees, and I can say what that SN representation that you can pull out of the dot action actually is. And for arbitrary graphs, I feel like I'm very close. Anyway, some interesting questions. The impression that I want to leave you about with this is that there are a lot of things about this construction that have yet to be explored. There are a lot of questions that you can ask, right? First, for what gamma is our gamma free? Why is that a terribly important question? So one of the requirements for GKM theory to work is you need your t-equivariant cohomology to be a free module over the polynomial ring, the t-equivariant cohomology of a point. So that example that we had before, we know it doesn't come from geometry, at least not directly in some sort of GKM fashion, because it wasn't a free module. So if you find a graph and it is free, but it doesn't directly come from geometry that you know, I would say that the first thing that you should look for is some sort of variety that spits out this as its GKM theory, or as its t-equivariant cohomology. One thing that I do have, at the very least, a decent amount of hope for is whether or not the SN module structure that we get from this will distinguish trees. in particular is it's stronger than the chromatic symmetric function for trees in terms of distinguishing between them. The third one's a little bit of a pipe dream, but the SN module structure on R gamma in the regular semi-simple Hessenberg variety case that I mentioned before has a correspondence with the chromatic symmetric function on the graph gamma. And I suppose at the very least it is an interesting question about whether or not that correspondence holds for any other graphs. And finally, and perhaps most reasonably, morally speaking, nothing I've said thus far shouldn't hold for finite reflection groups. You lose this whole graph gamma on 1 through n description, but take a generating set of reflections for your finite reflection group, draw your Cayley graph, see whether or not you can leverage the group structure in the same kind of a coset way to find generators for your module. Thank you very much. That's all I have.